The ship's engines sputter out, dead. Now you're being pulled toward the universe's ultimate monster, a supermassive black hole. In minutes, time will slow, space will twist, and every law of physics you've ever trusted will shatter. There is no escape, only the edge of reality itself. T-minus 9 billion years. The black hole destined to swallow you is beginning to take shape. The young Milky Way was forming in a swirling, chaotic web of stars, gas, and dark matter. Smaller galaxies are being crushed together, and gravity is sculpting the structures that will one day become home to our Sun. Deep within this cosmic chaos, the heart of a monster begins to form, a supermassive black hole that will one day become known as Sagittarius A, becomes the dark force at the center of our galaxy. But not all black holes are born the same way. Most black holes are stellar mass, born from the deaths of giants. When a star roughly 20 times heavier than our Sun burns through its fuel, fusion's outward push collapses. Gravity wins, crushing everything inward until space itself caves in, and a black hole is born. The core collapses, triggering a supernova so bright it can briefly outshine an entire galaxy. What remains is a black hole just 10 to 50 times the mass of the Sun. Incredibly dense, but still tiny on the cosmic scale. Sagittarius A is something else entirely. It's a supermassive black hole, an object containing over 4 million times the mass of our Sun, packed into a space smaller than the orbit of Mercury. Sagittarius A was born via a cosmic cannibalism. Over billions of years, it consumed everything that ventured too close, including stars, planets, and even other black holes. With each meal, Sagittarius A's gravitational well became larger and stronger. From the outside, it is deceptively quiet, a dark silhouette surrounded by a halo of plasma, glowing at millions of degrees. But beyond that calm surface lies a place where space and time are so warped that the laws of physics begin to fail. And in the distant future, 9 billion years after its birth, that is where you will be headed. T-minus 1 day. You've been traveling through deep space for months, the glow of Sagittarius A looming large. Now only 1 day remains before you meet the black hole face to face, all in the name of science. From this distance, it doesn't look terrifying, just a perfectly dark circle surrounded by a halo of fire, a glowing accretion disk of gas and dust heated to millions of degrees Kelvin as it spirals inward. But make no mistake, the most extreme object in our galaxy is lying in wait for you. Your ship drifts into a region astronomers call the strong gravity region, about several million miles from the black hole's event horizon. At this range, you've crossed the invisible threshold where gravity begins to noticeably pull on your spacecraft. It's gentle at first, but soon it's strong enough for your onboard instruments to go haywire. Gyroscopes spin erratically, and the navigation computer can no longer plot straight lines. It's here that space itself begins to curve significantly. Einstein's theory of general relativity tells us that gravity isn't a force pulling on you, it is the warping of spacetime itself. And Sagittarius A, with a mass over 4 million times greater than our Sun, bends spacetime so dramatically that light itself cannot escape. Then, you start to notice something strange. The stars behind you look normal, but the ones ahead of you seem to twist and smear around the black hole's edge, forming a perfect luminous ring. Light orbits the black hole before being dragged inward. You're now seeing the very edge of visibility, a region so distorted that the concept of up and down starts to lose meaning. Your ship's clock ticks normally, but if someone were watching you from far away, they would see something else entirely different. From their perspective, your time has already begun to slow down. According to relativity, as you get closer to the black hole, time dilation increases. A second for you might pass as 1.1 seconds for them. It's barely noticeable now, but as you get closer, time will appear to slow to a crawl. Every mile deeper you go into the gravitational well, time bends a little more. If you hovered safely at a distance of 620 miles from the event horizon, a minute for you might equal several minutes for someone far away from the black hole. If you get even closer, within a few hundred miles, an hour for you could equal years for someone watching from beyond the black hole's pull. Your ship's aft section begins stretching ever so slightly. Not enough to notice physically, but your sensors detect it and emit a warning signal. The gravitational difference between the front and back of your ship, known as tidal forces, is increasing. The closer you get to the singularity, the stronger those differences become. For now, you're calm, watching the black hole fill more and more of your view. Tomorrow, you'll face the edge of reality as we know it as you approach the event horizon. And once you cross it, there is no coming back. T-minus 10 minutes. If you've turned around right now and you've fired every thruster your ship has, You could theoretically escape, but barely. The black hole's gravity is so immense that even light itself would need to be following a precise path to get out. Your engines hum, but the ship feels heavy, sluggish. Out here, every foot closer to the event horizon increases the gravitational pull by enormous amounts. The gravitational strength between the front and back of your ship is growing by the second. It's not enough to tear you apart yet, but it is enough to visibly stretch the corridors of your craft. Panic starts to take over. You open a channel and send a radio signal back to the space station sitting just beyond the black hole's gravitational reach, where scientists watch your journey into Sagittarius A. The transmission leaves your ship at the speed of light. The carrier waves, modulated by your voice, bounce off the curve of space-time as they climb out of the black hole's immense gravity well. But there is a problem, a big one. As those photons travel away from your ship, they lose energy as they fight gravity itself. The wavelengths of your signal stretch, shifting lower and lower on the spectrum. To you, the signal sounds fine, but on the space station, everything is distorted. The space station adjusts its receivers, tuning lower and lower as your signal fades. The delay grows. What you said seconds ago is reaching the space station hours later. But even if they could respond instantly, what could the scientists do? You are only a few hundred miles from the event horizon, and your ship doesn't have the thrust to escape the black hole's pull. Inside your craft, time feels pretty normal. You're breathing fast, your heart rate is rising, but to the space station watching from afar, your clock is slowing. Each second you live stretches longer and longer in the space station's frame of reference. From their perspective, it's as if you are moving through molasses, and the closer you get to the horizon, the slower you seem to move. Meanwhile, the tidal forces keep increasing. The difference is still small, but it is climbing exponentially. Every second that passes, the gradient steepens, threatening to pull at the ship's structure more and more. You check the hull readouts. Minor stress fractures begin to register in the outer plating. Nothing catastrophic yet, but the warning lights are blinking. Outside your window, space itself is warping. The black hole now fills half of the sky. Inside your ship, you begin to feel the faint sensation of falling, though your instruments show no acceleration. That's because you are now in free fall. You are following the natural curve of space-time toward the singularity, and from this point on, there is no turning back. 0 hour. There's a calm before the chaos, an eerie, impossible stillness. From the space station, you look frozen, suspended in time just above the event horizon of Sagittarius A. According to their instruments, your time is nearly frozen. Every second for you is taking years, decades, or maybe even centuries for those observing you. But from your perspective, everything still feels normal. Your instruments are still blinking, your heart is still beating. You've just crossed the event horizon, the point of no return, where not even light can escape the gravity of the black hole. What this means is that you have entered a place where the escape velocity exceeds the speed of light, which is an impossibility since physics tells us that nothing can move faster than the speed of light. But you're not falling alone. Around you, other matter is drifting inward, such as gases, cosmic dust, and fragments of destroyed celestial bodies. Together, they have joined the accretion disk as a fast swirling storm of superheated matter spiraling into oblivion. That heat causes the material to emit intense electromagnetic radiation. In gentler cosmic environments, an accretion disk might glow softly in the infrared spectrum. Its radiation relatively low energy, but in the case of a supermassive black hole, gravity and friction crank the energy up to devastating levels. The radiation pouring off of the disk is high-energy X-rays and gamma rays. Your ship's sensors are flooded with static. Radiation alarms blare. The electromagnetic storm outside is unlike anything humanity has ever faced. Particles in the disk are moving at up to half of the speed of light. They collide with one another and generate jets of plasma that can stretch thousands of light years into space. And yet, at this moment, it feels silent. The sound can't reach you. It can't exist here. Space is almost a complete vacuum, and all of that chaos outside plays out in complete, crushing quiet. You watch through the viewport as the edge of the event horizon distorts the stars beyond, bending them into surreal arcs of light. The universe looks as if it's melting. From the space station, your image begins to redshift as the light reflecting off of you bends, casting a bloody crimson across your ship's hull. To everyone observing you from the outside, it looks like you have been suspended in time forever. But to you, the fall continues. You see the stars twisting above the blackness, swallowing the universe below. You are now inside the event horizon. The rules of the universe no longer apply in any way we understand. Outside, you will never be seen again. But for you, the journey isn't over. From this point onward, there is no going back, no calling for help, no slowing down. T plus 20 seconds. At this point, the gravity pulling at your feet is much stronger than at your head. And as you keep falling, the difference grows exponentially. A few thousand miles deeper, the gradient becomes lethal. The lower half of your body is being dragged toward the center faster than the upper half. Your bones, muscles, and even the molecular bonds that hold you together begin to stretch. It's at this point that you start to resemble spaghetti. And it's for this reason scientists call this process spaghettification. Your body is stretched into a long, thin thread of atoms, each one falling slightly faster than the one above it. You're elongated into a stream of matter hundreds of meters long, but only micrometers wide. It's not instant. In a supermassive black hole like Sagittarius A, the process might take several seconds before you're completely torn apart. That is to say, it would take long enough for you to feel it, long enough for you to understand that gravity has now become your executioner. However, let's pretend somehow you have survived spaghettification. Maybe your ship is made up of exotic matter, some theoretical alloy that resists infinite tidal stress. Unfortunately, you are not alone. Around you, more and more matter is falling into the black hole. It might sound comforting, having company in this dark abyss, but this is no peaceful descent. You watch as streaks of plasma spiral past your ship, glowing in a sickly blue-white hue before vanishing into the blackness below. The turbulence is violent and unpredictable. Magnetic fields twist the charged particles into knots, and the entire disk crackles with energy. Some pieces of the debris might be large enough to puncture the hull of your ship, exposing you to the void of the black hole. Every so often, immense magnetic forces at the black hole's poles redirect some of the material of the accretion disk outward. This results in a relativistic jet, where tightly focused beams of ionized matter blast out into space at near light speed. These jets are among the most powerful phenomena in the universe, capable of extending millions of light years and emanating more energy than an entire galaxy. And if you were unlucky enough to be ejected from the black hole in this way, your atoms would be scattered across the universe. Thankfully, you're not caught in one of them. Those jets form along the axis of rotation perpendicular to the accretion disk, and you've fallen in almost sideways, embedded within the disk's plane. Still, even here in the disk, the radiation is intense. The hull temperature climbs to thousands of degrees, and sensors overload as the electromagnetic noise spikes. If you could somehow pause and look around, you would see matter stretching, twisting, and glowing as it circles the black hole. The closer it gets to the singularity, the slower it moves, until eventually every piece of matter you can see will be torn apart and compressed into something infinitely small and dense. From here on out, physics begins to lose its meaning. Distance, time, and direction no longer behave as they once did. And as impossible as it sounds, things are about to get even stranger. T plus 40 seconds. By now, you are far beyond the reach of the universe you once knew. And this is where things start to get especially strange. The gravity of the black hole doesn't just pull on matter, it warps space-time itself. The deeper you fall, the more that distortion intensifies, bending reality into shapes that no human mind could truly imagine. What you're experiencing now is an extreme form of time dilation, a phenomenon predicted by Einstein's general theory of relativity. Time dilation is what happens when gravity becomes so strong that time itself slows down relative to an outside observer. Near a black hole, that effect is taken to its absolute extreme. The tidal forces have become unimaginably strong. Every atom in your body feels a slightly different pull, and that difference grows with every fraction of a second. At this point, the gravitational field isn't just tearing you limb from limb, it is overwhelming the electromagnetic forces that hold your molecules together. The bonds that once kept your atoms stable cannot withstand the differential pull. According to quantum theory, information can't be destroyed, only transformed. So, in a strange and unsettling way, every detail of your existence, such as your memories, atoms, and your very essence, is now encoded across the surface of the event horizon. You have become a part of the black hole. T plus 1 minute. You have reached the singularity. This is the point where density becomes infinite and space-time curvature becomes immeasurable. In other words, all the mass of the black hole, millions of suns worth, is compressed into a point smaller than an atom. From your perspective, this is the moment where space-time and space-time all collapse together. Inside of the singularity, there is no before or after. Time doesn't flow at all. Every direction leads to the same endpoint. You can't turn back or look forward. The concept of movement itself loses meaning. So what actually happens within the singularity of a black hole? One theory suggests that at the singularity, all matter is crushed into a single, dimensionless point. The gravitational forces are so overwhelming that they overcome every other force in nature, such as electromagnetic, nuclear, even quantum. Every atom of your being, every particle that ever made you, is forced into a single, infinitely small space. You cease to exist not as matter or anything else. There's also the loop quantum gravity theory, which proposes something even stranger, that black holes don't destroy information, but transform it. Instead of being erased, the data that made up your body and your mind might be encoded in microscopic structures of space-time, preserved forever. Some scientists believe that this could even explain Hawking radiation, the slow evaporation of black holes as they emit tiny particles over trillions of years. And then there's the wildest theory of them all. At the end of a black hole is the beginning of a new universe. If the laws of quantum mechanics somehow resist total collapse, the energy concentrated at the singularity could explode outward again, creating a new region of space-time. That means it's theoretically possible that every black hole in our universe might contain another universe inside of it, creating an infinite nesting doll of universes. If that's true, then right now, as you reach the singularity, your atoms could be torn apart, reassembled, and reborn in a new cosmos entirely. But until you've reached the singularity of the black hole you've fallen into, there's no way to know for sure what future awaits you. As far as we can tell, our equations say that the singularity is the end of time, the end of space, and the end of anything that reaches it. And yet, in the infinite gravity and infinite mystery of the singularity, there's a mind-boggling possibility that the end of your story in this universe is the start of a story in another. You've seen what happens if you fall into a black hole, but what about the other side of the cosmic equation? Watch What is a White Hole Opposite of Black Hole to uncover one of space's greatest mysteries, or click on this video instead.